Okay, today we are going to talk about vectors and the idea of vectors. Pause this video, take a second to look at this Paperman in 2D animation video. It's kind of cool how they're using vectors to animate characters. Um, Vectors we know have magnitude and direction. They help you to quantify positions and movement, and they provide tools for enhancing spatial awareness. So, our TOK connection. The comprehensions of vectors plays a large role in the development and innovation in regard to mechanized motion. Mechanics, perhaps more than any other area of knowledge, has a very diverse application area. Given that mathematics is the foundation for many other technologies and sets of knowledge, does this imply that mathematics is the best area of knowledge? It's a question to think about and ponder. Some people will probably say yes, some people will say absolutely not. Knowledge question. Should society place a greater emphasis on some areas of knowledge than others? Interesting thought to think about. Okay, the concept of a vector. A scalar is a number. A vector is a vector. If you want to watch the Despicable Me clip, you may, but otherwise, I think you probably know it. So categorize these as scalars of a vector. 3 kilometers northeast. That is a magnitude 3, a direction northeast. 2,000 calories doesn't have direction, just a scalar. 80 kilometers per hour, um, that is a scalar. It does not have a direction. Unless you want to say positive is in that direction and negative is in this direction, then it could potentially. Negative 15 degrees Celsius is a scalar. Again, doesn't have a direction. Running toward the finish line at 7 kilometers per hour. That has a direction. This is a vector. It's not specific, it's just towards the finish line from where you are. So that definitely has a vector. Okay. Directed line segments and vectors and displacement. Okay, notice AB goes from A to B and the arrow is pointing at B. BA versus the other one goes from B to A. The arrow is pointing at A. These are not the same vector. They're 180 degrees different. The starting point matters. They're not rays. They don't go forever in both directions, but the same idea as that of a ray. Okay, important things to note. Vectors, you must draw the line. When you write a vector, you must write it like that. You must draw the line above vector v. This book does a good job of having a lot of them. Sometimes they will indicate a vector v by just making it bold. You cannot make it bold handwriting, so you must draw the line above it to show you know that it is a vector. Okay, a line segment is not a vector. 3 non-collinear points determine a plane. That's an important property from geometry. We will be doing vectors in a plane and vectors in 3D space. The IB exam papers, textbooks, notation often use bold to denotate a vector, but you must write it with the line above it because you can't do bold handwriting. They won't know if it's bold or not. AB could represent a displacement vector, or it could end different type of vector. We're going to talk about lots of examples of vectors and vector notation. Absolute value around a vector indicates magnitude, or just how long it is. Find the magnitude of AB. I'm going to assume each one of the big things is 1. That's 3. This is 2. Define magnitude. You use the Pythagorean theorem. Square root of 13. I don't feel like getting a decimal. 0 vectors are vectors with magnitude 0. vectors do not have location, so A, B, and C are all going in the same direction with the same magnitude. They are equivalent vectors. Which of these are equal? A and D are equal. B is not, it's going in the opposite direction. C and E are also equal. A and B are called opposite vectors. Same thing, but opposite directions. Okay, knowing those terms and what they mean is important. Vectors here. Okay, important vector notation. So here we've got Milan, Athens, Sofia, Istanbul. So we can do IS, Istanbul to Sofia. So it looks like we're starting in Istanbul. We have a vector that goes here. I'm going to change my color. Show up better on this map. Then we have Sofia to Athens. Then we have Athens to Milan. So if we add them all together, we get Istanbul to Milan, which is this vector right here. It is the direct path, or the as the crow flies path. Really important to understand that when I add vectors, the sum is just connecting beginning to end, shortest path. So U plus V, and we call this tip to tail. U's tip goes to the tail of V. I could also do V and U. Apparently those are italicized and bold. I wish they would have put the arrows above. So the order with addition doesn't matter. With subtraction, like always, it does matter. And I don't believe in vector subtraction. I add negatives. I would never do U minus V. There's a special way of doing that. What I do is U plus negative V. Negative V is V, but going the opposite direction. That's negative V. So that is U minus V. That's important to notate and understand that notation. Again, I totally believe in adding negatives as opposed to remembering which one goes which way with the positives. So these vectors, A, B, B, C, C, D, D, A equals 0, the sum. They just add up. So draw a vector representing A, B, C, D. So to make CD here, I got to move it. Looks like it's going back 3 and up 2. It's got to end up there. That's D now. And EF. This is also E. So my sum vector looks like that. I could do CD, then AB. This would also be an AB. And then EF. So you're going to notice that no matter how I do this, my sum vector is still the same here. It's the blue one there, the red one here. And I move the vectors around. I can add them in any order. I get the same thing. You likely will not have a question this simple, but sometimes the drawing of vectors is useful in other problems. I showed you the parallelogram thing. Multiplying vectors by a scalar and parallel vectors. Multiplying a vector is a plus 4a, you just add them together, it's 4 times as long. The magnitude changes, the direction does not. So write these in terms of a. V looks to be 1/3 a. W looks to be 2/3 a. That's a. T is twice as long as a, and it's going in a negative direction, so it's negative 2a. Yeah. And again, make sure to put the arrows about. Okay, in triangle ABC, points D and E are midpoints of AB and BC. If AB is vector A and BC is vector B, show that DE is parallel to AC. So DE is parallel to AC. So I can say here that AB, if I'm thinking in terms of vectors, plus BC is equal to AC. Well, since vectors have no location, 1/2 AB is equal to DB. And we know that DB plus BE is going to equal DE. I also know that 1/2, because these are midpoints, 1/2 BC equals BE. So 1/2 AB plus 1/2 AC should equal DE. I'm just substituting. And I can factor out the 1/2. No, that's BC. I wrote this wrong. BE is 1/2 BC. I need to substitute correctly. AB plus BC is AC. These are parallel, and I'm not going to write it, but these are parallel because AC times a scalar is equal to DE. Okay, we're going to now talk about component form of a vector. And component form, you should have a pretty good idea what that is. And component form is essentially going in the, so I go here, that's down 2. It's essentially making a right triangle. Generally, you want those to be horizontal and vertical. Doesn't have to be, but usually doesn't make a lot of sense to not. This is going in a negative direction and a negative direction. So we've in the past written this as -2, -6. The I and j unit vectors are -2. No, I did that backwards. -6 is my horizontal, -2 is my vertical. -6 I hat. This hat means unit vector, so it's vector of length 1. The I unit vector is in the horizontal direction. This is -6 horizontal units of 1. -2 j hat being the vertical. The third dimension, like coming out, would be k hat. And you could write this with 3 like this. Or there's another vector notation that we're going to use a lot. And it's kind of like a vector is like a one-column matrix. -6 in the x direction, -2 in the, I'm missing the negative, -2 in the y direction, 0 in the z direction. And those are my unit vectors. So, example 2 here. Points A and B have position vectors A and B respectively, relative to a fixed origin O. Write the vector AB in terms of A. So I know my vectors somewhere here, little a. That's point A, point B, so that looks like subtraction when they're tail to tail. If I put B going here, that'd be -B, and I would get an equivalent vector. So this is my vector AB equals A minus B. Now they got it as B minus A. They put a point here. A goes from the origin to there. B, AB is B minus A. Oh, yep, it's B minus A. I went the wrong way. Should have started at the origin. This vector would have went this way. Should have started at the origin. So it should be B minus A. It's important to start your vectors at the starting point. Don't make up a new starting point. It's not a return vector. It's from start to end. So adding vectors, you add the x parts, you add the y parts. So you got 2 of them, you add the z parts. You multiply by a scalar, the scalar multiplies by all the parts. Okay, so nothing changed really going from 2 to 3 dimensions. You just add the x parts, multiply the scalar here. Component form of vectors is super useful. It allows us to break things apart and perform the math separately. So here I have given them a u plus v. So I'm going to essentially add the i's. 3i, I'm going to leave them an I. 3j minus 1j is 2j. And there's no k. So this would be 3, 2, 0 would be another form of writing that. U minus 2v. So let's figure out 2v equals -2v. We'll just add them then. -2i hat plus 2j hat minus 2k hat. So that u minus 2v, 2i minus 2i is 0i. 3j plus 2j is 5j hat negative k minus 2k is negative 3k hat. Or, in probably my preferred form, 0, 5, negative 3. And there it is. So for A and B have position vectors respectively. Point C lies on the line segment AB. If AC is a 2-to-1 proportion, find the position of vector C. So AB as a vector is 1 to 2. Well, so that's 1, 4, and negative 5. So I've got AB, find the position vector of C, CB. So that's AB. I'm going a third of the way essentially because it's 1 to 2 from AC to CB. So it's something like A, B, C is here. So I'm going to take my vector, multiply it by a third, and negative 5/3. This is my gut. And then I'm going to add that to my initial one, 1, 1, 1, 4/3, 7/3, negative 2/3. That's my gut, what my gut tells me for this. Let me check. I'm not sure how they did this. Yep, that's right. So yeah, I found the vector from A to B, figured out that it was 1/3 of the way, and then add it to the original. That's really important. Okay, example 5. These two vectors are parallel. Find the values for A and B. So if I know they're parallel, they're multiplied by a scalar. Well, in order to get this to be negative 6, the scalar's got to be negative 2. So A equals 4. That's a 4. And B equals negative 2. Okay, magnitude of a vector. Component form. Magnitude is just essentially the Pythagorean theorem. Square root of x squared plus y squared instead of having a squared. So there's also magnitude, the three-dimensional Pythagorean theorem. Square root of x squared plus y squared plus z squared. So if I want the magnitude of this vector, magnitude of W, I notated it like that. Square root of 2 squared plus 3 squared plus 6 squared. 4 plus 9 is 13 plus 36 is square root of 49, or 7. 7 is my magnitude. That wraps up today's lesson. We'll pick up with the rest of the section tomorrow.